Welcome to this session on regression. As part of SAP BTP AI best practices, we'll explore how to efficiently identify patterns and data using SAP HANA machine learning tools. By the end of this session, you'll have a clear understanding of key principles, best practices, and implementation approaches to uncover relationships between variables in your data. Our discussion will follow these 4 key steps. First, we'll provide an overview of regression and its benefits in the SAP ecosystem. Second, we'll cover the essential prerequisites you'll need to have in place, including supported environments and required components. Third, we'll explore key choices and guidelines that impact your implementation, including model evaluation to understand how well a model is performing, therefore helping to identify areas for improvement and guide model selection. Finally, we'll dive into implementation approaches across programming models, providing concrete examples for Python and SQL. Regression is the process of finding the best fit for a set of data points, essentially summarizing the relationship between 2 variables. In the SAP ecosystem, this involves leveraging SAP HANA ML or machine learning tools, specifically Predictive Analysis Library and HANA ML. The expected outcomes include predicting the value of the dependent variable based upon the independent variables, allowing for the identification of which independent variables are most influential in predicting the dependent variable. Optimizing business processes by helping to identify factors that influence key performance. Indicators test hypothesis and find optimal input values. Why use SAP HANA ML for regression? There are 3 main benefits. First, algorithm interchangeability. You can easily switch between different algorithms like linear regression, online linear regression, hybrid gradient boosting regression, or RDT regressor, to best suit your specific regression needs. Second, out-of-the-box features that supercharge your development with built-in capabilities for generalized linear models, decision tree-based modeling, among many others. Third, security and SAP ecosystem integration. It's fully integrated with SAP technologies, leveraging enterprise-grade security and native in-database processing. These advantages make regression more efficient and accessible for SAP users. Before implementing regression solutions, let's cover the necessary prerequisites. You'll need SAP HANA Platform 2.0 SPS 04 or higher, or preferably SAP HANA Cloud for easier management. SAP DataSphere or Express Edition can also be used for specific scenarios. Application Function Library contains Predictive Analysis Library and Automated Predictive Library components. Script Server enabled for executing ML algorithms. To provide more context, SAP HANA is an in-memory database enabling real-time analytics and applications. The HANA ML libraries, Predictive Analysis Library, and Automated Predictive Library provide native in-database functions for predictive analysis and machine learning. The script server is an auxiliary HANA process essential for executing these ML functions. Setting up these prerequisites establishes a strong foundation for implementing effective regression solutions at scale. Let's examine the high-level reference architecture for regression using SAP HANA ML. The diagram shows the complete ML execution environment within the SAP HANA ecosystem. At the core is the SAP HANA database hosting the Predictive Analysis Library and Automated Predictive Library. These provide the core regression algorithms. This architecture ensures efficient, scalable, and secure time series forecasting while leveraging the performance advantages of an in-memory database. Let's discuss key choices that impact the performance of your regression scenarios. Model performance metrics are crucial for evaluating and comparing the effectiveness of machine learning models. They provide a quantitative measure of how well a model is performing, helping to identify areas for improvement and guide your model selection. Common metrics specific to regression tasks are the following. R² is also known as coefficient of determination and denoted as R². It is basically the proportion of the variation in the response variable that is predictable from the independent variables. That is, the larger the value of R2, the more variability is explained by the model. Typically, R2 values vary from 0 to 1. The root mean squared error is the square root of the mean squared error. The mean squared error is computed by taking the mean of the squared differences between each actual value and its corresponding predicated value. A lower root mean squared error value indicates better model performance, meaning the model's predictions are closer to the true values. When making decisions based upon the forecast of regression models, confidence intervals may also be meaningful. A confidence interval is the mean of your estimate plus and minus the variation in that estimate. That is the range of values you expect your estimate to fall between within a certain level of confidence. Additionally, predictive analysis library supports both confidence and prediction intervals for models like generalized linear models and multiple linear regression, allowing users to assess not only the expected outcome, but also the uncertainty around individual predictions. It is crucial to select independent variables that are logically related to the dependent variables and can contribute to the prediction. For example, if you're predicting sales, you might consider factors like advertising spend, market price, and competitor activity. Consider domain expertise when selecting features, as some features may be more important than others from a business or scientific perspective. Data quality is fundamental in machine learning because poor data leads to inaccurate and unreliable models, ultimately hindering decision-making and predictions. Machine learning models rely on data to learn patterns and make predictions, so the quality of that data directly impacts the performance of the model. Thus, ensure independent variables are accurate, complete, and free from errors or outliers that could distort the analysis. Data cleaning, outlier removal, and normalization are crucial steps in preparing your data. Ensure sufficient data points, especially considering the number of independent variables and the noise level of your data. Validate imputation strategies and model fit using techniques like cross-validation and residential analysis. Feature selection is the process of choosing a subset of the most relevant features from a larger set to use in a model building. It's a crucial step in machine learning that helps improve model performance, reduce computational cost, and enhance interpretability. In this regard, consider techniques like feature importance analysis or model-based selection to identify the most relevant predictors. The former provides insights into which features are most influential in the model's output, allowing for better understanding of the data and the model performance. Several methods exist, including permutation, importance, shapely additive explanations, sharp values, and built-in importance scores from specific models. For example, sharp values offer a way to understand feature contributions by considering all possible combinations of features and calculating their marginal contributions. Let's discuss implementation guidelines for selecting your programming model. For data science workflows, we recommend using Python, with the Honda ML library providing a streamlined, intuitive experience aligned with standard data scientist practices, including convenient data manipulation and integration with machine learning workflows. Alternative approaches consider SQL script to directly call predictive analysis library procedures when tight integration with SAP HANA artifacts is needed. Let's explore the specific implementation options for each programming model for Python developers. The HANA ML library is recommended for interacting with SAP HANA Predictive Analysis Library and Automated Predictive Library algorithms. Reference code includes SAP BTP AI best practice sample code and SAP community blog posts like machine learning linear regression definition implementation scenarios in SAP HANA. For SQL developers, direct invocation of predictive analysis library procedures through SQL script is available. When embedding logic within SAP HANA artifacts is a priority, reference documentation includes comprehensive guides for diverse algorithms. Each approach provides full access to regression capabilities while allowing you to work in your preferred environment. The Python example demonstrates implementing the hybrid gradient boosting tree algorithm for regression using HANA ML. The SAP HANA Predictive Analysis Library hybrid gradient boosting tree algorithm is an SAP HANA optimized gradient boosting tree implementation supporting mixed feature types, continuous and categorical as input. It supports regression in classification scenarios. The hybrid gradient boosting model for regression is trained based upon the training subset, as shown in the figure. The training process requires just a few lines of code. This implementation showcases how quickly you can deploy powerful regressions with minimal code using SAP HANA machine learning. This best practice guide reflects the collective expertise of data scientists and analysts specialists from across SAP, bringing together insights to support your regression journey. Thank you for watching this session on regression using SAP HANA machine learning. We hope the information provided helps you successfully implement effective regression capabilities in your business applications.